Who is going to record it?
What are the record? No.
Okay. Okay.
Okay. Hello everyone again. Our speaker today is Dr. Phan from US, and you can see that in his slide. He said today is May 11 or 12, depend on where we are, right? Where you are, welcome Hùng to Australia virtually. Hùng received his PhD degree from Wayne State University under the supervision of Professor Boris Murokovic. He then became a postdoc at the University of British Columbia and University of Victoria in Canada, working with Professors Haibowski, Son Wan, and Zhen Yi. He now working at the University of Massachusetts Lowell. And today he will he is going to talk about adaptive splitting algorithm. It's your turn now.
Thank you, Ming, for a very warm introduction, and thank you all the organizer to provide the opportunity for me to be here. And I hope to visit Australia sometimes in the next few years, definitely. Right. So my talk today will be the adaptive splitting algorithms. This is based on joint work with several collaborators, and Ming is one of them. Sadie Bart, my colleague at UMass Lowell, Ruben Campoy, who in the University of Valencia now, and also Valentin Kaut, an engineer at Autodesk. So my talk is on May 11. I should give it like N12, so I give a talk for 2 days, right? All right, so let's get started. Let me move to the next slide. So my talk contains several parts, and hopefully it won't take too long for each of them. The introduction, and then the classical Douglas-Rachford algorithm. I will explain the structure of that, quick application, and convergence analysis. And after that, I will move on to our recent work in an adaptive Douglas-Rachford algorithm, which we denoted by little a and dr. I hope nobody got offended if we put a little a in front of the algorithm. All right, and also we did it the second time, an adaptive alternating direction methods of multipliers. So little a, ADMM. Okay. So for the introduction, from now on, X will be a Hilbert space, and we denote the subdifferential of F by this notation. It contains of all the subgradient. The basic subgradient in convex analysis is defined by this property. Okay, so the convex inequalities, the indicator function, and the subdifferential of the indicator's function will be the normal Cohn operators. So since this is the optimization seminar, I hope everybody already acquainted with this. And I will move on to the next slide. The FEDMA stationary condition when we work on a general optimization problem, in particular the minimization problems. Suppose I have function f and g, or just a function f is a proper lower semi-continuous convex function. When we minimize the function f over the full domain, little x in capital X, the sufficient and necessary condition is that either either the gradient will be 0 in the case f is differentiable, or 0 is in the subdifferential of f at the point x bar. Move on further from this, if we solve the minimization of the sum of two functions, we only have one way, one implication from the right-hand side to the left-hand side. Okay? we will try to find a point x bar, so that 0 belongs to the subdifferential of f at x bar plus the subdifferential of g at x bar. And this is a very general model which includes many other problems. Another is almost as important as the one we just talked about, is the minimization of a function over a domain omega. And omega here is a closed convex set for simplicity. Of course, we can always generalize omega to be just a closed set where we're going to have the local minimization necessary condition and so on. But over here, I simplify things and I keep as minimal as possible. So in order to minimize this problem, we convert it into the minimization of sum of two functions. One is the function f, and the other one is the indicator function of the set omega. And again, we use the Fermat stationary condition. We will try to find a point x that is the solution to this inclusion. 0 belongs to the subdifferential of f at x bar plus the normal cone of omega at x bar. And of course, this also applies to the problems of finding a point in the intersection of the two sets. So all of these are all related. So in general, we may consider an inclusion problem. It seems convenient for many class of problems. We will consider the inclusion problem finding an x that such that 0 belongs to the inclusion, belongs to the set ax plus bx, where a and b are just set values operators. Right, I will move on to the next slide. And, I will describe the Douglas-Rachford algorithm in a geometric way. But first of all, we will talk about the resolvent and the relaxed resolvent. Let A be an operators. The resolvent of A is defined by the inverse operators of the indicator function plus A. And the reflected resolvent, we will take the reflection of the resolvent over, of the reflection of the original point over the resolvent. So 2JA minus identity. And we also relax this concept by using a parameter lambda greater than 0. So the lambda relax resolvent of A is defined by the linear affine combination between the identity and the resolvent. So in order to illustrate the resolvent by some pictures, let's try to analyze the concept of the resolvent. So y belongs to JAX can be rewritten by definition first, and then by equivalent, we have x belongs to y plus ay. So that means given an x as the input, we will try to find an output y so that you can go back to the point x using a vectors in ay. Okay, so y is the output. And z here is the reflection image of x about y. So you can write down it as 2y minus x. So in this case, that's going to be r a x, and the point y here is JAX. Okay. So the relaxed resolvent is anything in between or even outside of z if we take lambda large enough. For example, if I take a point right here, this point will be a relaxed resolvent with the parameter, for instance, here could be, well, be 1.5, okay? And so on and so on. If you take j equals 3, you would end up at the point outside here, that would be JA, for instance, 3x. So the superscript here is not the exponents, it's just the superscript that represent the lambda. We couldn't find other notation that looks better. So for us, this looked reasonable. Okay? And Ming and I has worked on this relaxed resolvent on several projects. All right, so the resolvent is actually a generalization of the projection. So if the operator is the normal Korn operator, the resolvent of the normal Korn operator will be precisely the projection onto the set omega. And many class of operators will have a form of a way to compute the resolvent, and that has been known by many researchers as well as engineers. All right, I will move on to the next slide. So now I will describe the Douglas-Rachford algorithm. The algorithm will generate a sequence in the rule of xk plus 1 equals t xk, where t is 1/2 of the identity plus the reflection over A composition with the reflection over the operator B. So here is the diagram. I'll start, for example, at xk. The first point is y. We are going to find a point y, which is JAX, JXK in this case, but I will drop the subscript, right? And the green, the blue vector will be a vectors in AY, as we explained in the previous slide. After that, we will take the reflection. This is going to be RAX. And then from this reflection, we define W, going to be the resolvent of B, sorry, the resolvent JB of the point Z. Okay. And after that, we take a reflection. Then that will be RB, RA, X. Okay. And in keeping the, well, we're not done yet. Then we take the average. So xk plus 1 will be T xk, the average of xk and T. So when we keep iterating, and in the hope that the method will be stabilized at some fixed point. So whenever xk plus 1 equals xk are at least close to each other, then you can see that the triangle here collapse, and the point y will be the same as the point w, for which you will see that the red vector and the blue vector will be opposite. And these two vectors belong to AY and BW. So that's why 0 belongs to the sum of AY, BW. That means we have found a solution. So that's the general idea of the Douglas-Rachford algorithm. And there has been so many works on the Douglas-Rachford algorithm, and it would be easily overlooked at some work of somebody if I list all the names here. And I don't think I even have enough space to list all the mathematician who has been working on the Douglas-Rachford algorithms. Right, so I will move on to the next slide. So if we have a sum of finitely many operators, we can translate this problem using product space techniques, where we define the bold operator A by the product, the Cartesian product of the operator A1 to AM, and the operator B will be the normal Korn operator to the diagonals. Okay? And it turns out that 0 belongs to the sum of A1 until AMX is equivalent to 0 belongs to the sum of AX and BX. This should be the capital X. Okay? x here. This x here will be x1, x2, xn. And so we have done one part that convert the problem of finitely many operators into two operators, and then we can compute the resolvent for the Bone operator A and Bone the operator B. And in fact, this is exactly what we used in our application, for which I have worked with Valentin Couch, an engineer at Autodesk, where we try to design an object using spatial constraint, the geometric constraint. In this case, we, for example, we design a grading of a parking lot or building pad. And the constraint for the engineer is at least they need to find a feasible plan for the parking lot or building pad that fit with existing structures, the drainage requirements, safety condition, and they don't want to do much, right? So they want to change as little as possible, right? And in order to do so, we construct a model based on the triangular irregular network, okay? And we will adjusting the height of the vertices in this triangulated grid. Okay, so long story short, I will move on to the design of the view of a construction site. Right? So some of you may already see this before, so I will go. I'll promise to keep it short and concise. So here you can see the triangular network consisted of many triangles, 2D view, about 5,000 vertices or 7,000 triangles. It's not a big, not a big sample. Okay? The engineer has been working with a much bigger map. And the 3D views, you can see each of these points have the height. I'll call it Zi, okay? And Zi can go up or down as long as we want, right? For any of these. Only the XY coordinate is fixed. Okay? This is XY coordinate is fixed. Okay? So our variables are just the elevation in the n dimensional from Z1 to Zn. And all of these triangles are interconnect in some way. And from there, we will make all the constraint and the objective function into a model of optimization. The constraint, there's many different constraints I can list here. Interpolation constraint means that some values are predetermined. You cannot change that, they has to be fixed. The slope constraint on the edges, the alignment constraint on the edges, the low point constraint where you want to put a drain on the map. So that should be the lowest point. Right? And every point around has to flow, well, had to be higher than this low point. And also the surface alignment constraint where you have the slope for each triangles. You can align two triangles to have the same slope, or you can align the slope cannot be larger than something or smaller than something. Right? So we have two kinds of slope. For the maximum slope cannot be too steep, and the minimum slope to allow for the rain water to flow away. Okay, otherwise we're going to have a puddle of water in the middle of the ground. The lot. That is not nice. Right? And the cost function could be earthwork total volume. You need to cut and fill over them on the map, and all the net volume where you can use dirt from cutting. Okay. And for all of these, you're going to see we're going to have an objective function composed of several functions and constraint also. And the blue description here is simply the written out algorithm for the product space. Okay, so are you still following me? Is the connection good? Yeah. All right. So now I'm going to share another screen, a little bit of internet entertainment, I guess. So here's a little video. I hope you can see the map that I show, and this is made by Autodesk engineers. The designer will add the constraint and will run the algorithm. It is actually the Douglas-Rachford algorithm to minimize the grading curvature and to satisfy on the slope constraint and alignment constraint, as you can see on the map. And what they actually implement is the Douglas-Rachford algorithm. Okay. Okay, so now I'll be back to our talk, the mathematical part of it. The convergent analysis of the Douglas-Rachford algorithm. And certainly we will need monotonicity and firm non-expansiveness. Monotonicity is strongly related to convex function, and the precise definition is straightforward. An operator is monotone if the inner product between 2 points on the graph, not the difference between 2 points AB, inner product with the two images, U and V, is greater than or equal to 0. So I make a simple graph to illustrate what happened with the monotone operator. Suppose you have 2 points, A and B. I'm going to use different colors. So we have point A and B. U and V are the image. U is in A, and V is in AB. And the difference between AB is this vector. The difference between U and V is this vector, and the inner product is greater than 0, means that the angle created by these two, sorry, it's not this angle. That is this angle, right? Will be less than 90 degrees. And A is maximally monotone if no monotone operators A hat that satisfy this property. That strictly includes the graph of A. The operator T is firmly non-expansive. If for all x, y in the domain of T, we will have this inequality, the distance between Tx and Ty will be no more than x, the distance between x minus y squared in this case, and subtract by an amount of the difference between them. So if I illustrate by the picture, if I start with the 2 points, x here and y here, if I start at a point x here and y here, my Tx and my Ty should be closer than the original point, the original distance at the first, at least. But even more, they has to satisfy this inequality, for which if I draw the diagram, we're going to have the triangle with 3 edges like this, and we must have an obtuse angle at this place. So in this case, if you write down the triangle inequalities, not exactly the triangle inequality, just the sum of square. In this case, we're gonna obtain precisely this inequalities. So they are actually related by the following relation. A is monotone if and only if the inverse of identity plus A will be firmly non-expansive, which is the resolvent resolvent of A. Okay? And that will be part of the ingredients that we're going to use to prove the convergence for the Douglas-Rachford algorithm. All right, so convergence analysis, I just quote three notable results. One of the most important results is due to Lyons and Mercier in 1979, saying that if the two operators are maximally monotone operators, such that the zero of the sum is non-empty, then the sequence generated by the Douglas-Rachford algorithm will converge quickly to a fixed point. And from that fixed point, the resolvent of A of that fixed point will be the solution to the required problems, okay? The zero of the sum of two operators. And it turns out, interestingly, that not until 2011, that spider proved that the shadow sequence, JAXK, also converge quickly to JAX bar. The proof is, I think, is very neat, but very technical, and somehow followed. It's hard to follow. And then in 2013, Hans Bauski, my former postdoc advisor, proved the same result, which is based on the Demi-Clonis principle. The proof is very accessible, I think, and fairly easy to follow. We will be back on the Demi-Clonis principle at a later point in these presentations. So, but these are the three results that that motivate us to construct our results. Okay. Now let me move on to the next part, where I will talk about the adaptive Douglas-Rachford algorithms. So in the adaptive Douglas-Rachford algorithm, we will modify the original Douglas-Rachford operators as follows, as described. So the iteration is defined by xk plus 1 equals tx, where the operator t will be 1 minus kappa identity plus kappa r2, r1. So R2 is the second reflection, more or less, and R1 is the first reflection. This is the way we denote it. Kappa here, for most of the part, we can simply use kappa equals 1/2. But of course, the range of kappa could be more than that. So we define J1 is the resolvent over A with the parameters gamma. J2 is the resolvent of B with the parameter delta. The two different parameters. R1 is the relaxed resolvent R2, of J1. R2 is the relaxed resolvent of J2 with two different parameters, lambda and mu here, you can see. So in total, we have 4 at least. So gamma, delta, lambda, and mu. So let's see how we generate the sequence. Again, starting from xk, you can see from the picture, we generate the first point is y. Then we make a relaxed resolvent, z. From there, we take the second resolvent to w, and then move back to t. Then taking the convex combination, the affine combination to obtain x equals, to obtain xk plus 1. Okay. So in this picture, I deliberately choosing lambda equals 3. So I will make one further step away from the reflected resolvent. To compensate for that, when I make the second reflection, I'm going to use mu equals 1.5. The reason for doing this is I want to create a similar triangles, two similar triangles. In this way, when t and when when xk plus 1 and x coincide, I will also have y and w coincide, for which I will generate two vectors in the opposite direction, and then only the matter of scaling will give me the zero sum. Okay, so that's the whole point of the adaptive Douglas-Rachford algorithm. And you can see from here, with lambda equals 3 and mu equals 1.5, you can check that lambda minus 1 times mu minus 1 would be 1. Oops, it's like flashing. I hope it's not a problem. Okay? And that's why you see we have a condition here. Okay, and also you can see the red vector will be double the size of the blue vector, which is what we want, and therefore not exactly what we want. Therefore, we need to put the scaling parameters gamma and delta so that they eventually I will obtain a 0 in the sum of ay plus by. In this case, bw is y. And so you can see here, you can check that delta would be 2 times gamma, which is lambda minus 1 gamma. Right? And of course, if lambda equals mu equals 2, then the adaptive Douglas-Rachford becomes the classical Douglas-Rachford. All right. So where do we use the adaptive Douglas-Rachford, and can we guarantee convergence? I'm halfway, and hopefully. Okay. The adaptive Douglas-Rachford will be used in the situation where we have generalized monotonicity and or generalized co-monotonicity. Given a number alpha, we say that A is alpha monotone if the inner product we composed by the difference between the pre-image and the difference between the image is greater than alpha times xy minus x minus y squared. And alpha comonotone if we have the similar inequalities, but on the image side, where you have u and v on the right-hand side instead of x and minus y. And similar concept for maximally alpha monotone and maximally alpha comonotone, if you cannot make it bigger. Okay? And when alpha equals 0, both of these concepts become just monotone. Alpha greater than 0, we will include the words strongly in there. So strongly monotone or strongly comonotone. Strongly comonotone is actually co-coercive in the monotone operator theory. And alpha less than 0 is weakly monotone and weakly comonotone. And our setup is to apply the adaptive Douglas-Rachford to the problem, the inclusion problem, where A and B are maximally alpha and beta monotone, or A and B are maximally alpha and beta comonotone. And the parameters that we require is alpha plus beta is greater than 0. So in all, the original problem is convex. Okay. Okay, we would like to make a note before we proceed. A note about the weak and strong monotonicity. We can check that if A is alpha 1 monotone, then when you add an alpha 2 identity into A, we will have alpha 1 plus alpha 2 monotone. So if A and B are alpha and beta monotone with the sum greater than 0, then we can modify the sum of two operators by adding and subtracting the same amount of identity from them to obtain the A tilde and B tilde, so that A tilde and B tilde are both monotone. In particular, they are both monotone. Okay? This parameter is greater than or equal to 0. Therefore, if we modify the operator A and B, we will convert the problem into an equivalent problems. 0 belongs to A tilde x plus B tilde x. And we can use any available tooling for the monotone operators. For example, the classical Douglas-Rachford algorithms. But anyway, we want to proceed with the original operator A and B. Let's see if it works in a similar fashion or not. Okay. So Ming and I has worked on this project for a while, and our first result comes out 3 years ago, I think, the time we submit the papers, and we verify that if you choose the parameters gamma, delta, lambda, and mu in certain range, okay, then the sequence generated by the adaptive Douglas-Rachford algorithm will converge weakly to a fixed point, and the resultant of that fixed point is a solution to the original problems. In our first paper, we consider two cases separately, and there's a reason for that. And later on, we found out that there's actually a gap between the two, that the two cannot cover each other, and we improve it by a later project where Ming and I and Sadie work on another papers. We try to we cover the gap created by these two results. Okay. Okay, so the gap is created by when we look at the proof. So under the assumption, we will obtain a similar inequality for the operator T, just like the firmly non-expansive, and we want T at least to be every terms on the right hand side except x minus y will decrease the bound for Tx minus Ty. So that's why we require this term to be positive, and this term to be positive as well. So that's why we require mu to be within these two numbers. And then later we find out that we can borrow a little bit from the term here to compensate for the case if we don't have both positive in the last two coefficients. And that will fill the gaps. And we're going to see it in the next slide. Not exactly. Okay, before we move on, I want to mention that the result is applied when we apply for a strong monotone operator A and a weakly monotone operator B. And it turns out that if A is strong, we will under reflect. Okay? That means we're going to use lambda less than 2. And for operator B, we will use mu to be greater than 2 to go back to a suitable position, so that we're going to create the fixed point for these operators. Okay, so in the follow-up work, which Sadie and Ming and I work on, we provide a different perspective for the convergent analysis of the adaptive Douglas-Rachford algorithm using the conical averageness concept. To let theta greater than 0, we say that T is conically theta average if T is an affine combination between the some non-expansive operators and the identity. So if theta equals 1, we have non-expansive. If theta is 1/2, it is precisely firmly non-expansive. And if theta is between 0 and 1, we have the classical average operators. And the analysis will be based on the composition of two conically average operators. If we have two conically average operators that satisfy certain condition, then their composition T with the incorporation of a parameter omega will also be conically theta average. It doesn't matter the order of T1, T2, you can actually flip the position of T1, T2, and we still have conically theta average with certain parameter theta. And that is also a key property to develop the adaptive Douglas-Rachford algorithm for both monotone and co-monotone operators. So based on these two results, the result, we developed the result for maximally alpha monotone and maximally beta monotone operators. And you can see here, the range is a bit different from what we see before. So before, mu is between 2 plus 2 gamma alpha and no less than 2 minus 2 gamma beta. And certainly you can see the right-hand side here is an improvement, even though by an epsilon, but that will cover the gap between the two results, for which we can combine them into a single result here, as you can see. And the lower bound is different, completely different appearance, and the new one is also better than the previous one. We also obtained the conversion, the width conversion to a fixed point as well. And similarly, without much of change, we can also obtain a similar result for the co-monotone operators, maximally monotone operator, co-monotone operator A and B. And the conclusion is similar, which is expected. Okay. So that conclusion for our second work. Next, I will talk about the demi-clonus and the width convergence for the adaptive Douglas-Rachford algorithm. So you can see, I haven't mentioned the width convergence of the shadow sequence. In this case, we actually talk about the shadow sequence. And we will develop our result based on the result by Hans Bowski in 2013, the demi-clonus principle for formulating expansive operators, written as follows. If we have two sequences, X and Z, they are both converge weakly to X star and Z star, so that their image T1 XN, T2 ZN also converge quickly to Y star, and then another condition, and then another condition. Just so many conditions. If they all satisfy, then Y star will be T1 X star and T equals T2 Z star. I leave a big space here, actually on purpose, so that I can draw some diagram. This is how I look at this result. I'll start with a sequence XN converges quickly to an X star, and I have another sequence ZN converges quickly to Z star. The two images, T1 XN to T1 XN, and then T2 ZN, both of them converge weakly to a Y star. And their difference, the sum of the difference. So I'm going to use red here. The red vector here, sum up with the red vector here, converges to the sum of these two vectors. Okay. And also the difference, the vector difference between T1XN and T2ZN converge strongly to 0. If all these satisfy, then Y star will be T1 of X star and T2 of Z star. So how I resemble this with the Douglas-Rachford algorithm, you can see here this XN Zn will be precisely the reflection, resolvent over A of xn, and J1 xn, JAxn will be T1, and JB of Zn will be T2 Zn. Okay. So these are the structure of the Douglas-Rachford algorithm. And based on this, I think it's a very elegant design, even though there's so many conditions. However, it fits nicely with the Douglas-Rachford algorithm. From there, we will prove the weak convergence to the shadow point. Okay, so based on that, Sadie and Ruben Campoy and I work on a project that we developed the Demi-Clonist principle for co-coercive operators. So keep in mind that Fermi expansive is equivalent to 1 co-coercivity. And at first we think that it's simply a replacement of some parameters in the original resolved by Hans Bowski. However, it turns out a little bit interesting that we need to tweak quite a few things to make it work. And one of the things we need is to impose a balance condition. If we have sigma 1 and sigma 2 co-coercive, and suppose we can find a parameter rho 1 and rho 2 that satisfy this condition, so that all of these conditions satisfy. The black one is precisely the one from Hans Bowski's results. The blue one is a modified one where we don't have the planned summation, but we weighted with the parameters rho 1 and rho 2. And as you can expect from the adaptive Douglas-Rachford, we don't have equal weight. Okay? So this is xn and this is zn. The weight would be different. Okay? This is T1 xn, T2 zn. So more or less, we need to multiply this by rho 1 and this by rho 2 to make it works. All right, and we also have similar result for average operators. And then we also need some balance condition here for these two operators. And it is pretty expected that we work this out, even though the details are a little bit different from the previous result. And using these two Demi-Clonist principle, we prove the convergence for the shadow sequence. So if we have two maximally alpha monotone operators, one is maximally alpha monotone and maximally beta monotone operator, we can prove the shadow sequence converges to the solution weakly. And suppose the parameters are chosen appropriately. I skip the detail how you choose it, and of course, it is written in the papers as well as in the previous slide. And I'll just say chosen appropriately. And at the same time, if we work on co-monotone operators, then we have the similar results that the shadow sequence will also converge weakly to a 0 of the problem. At first, when we developed these two results, and the reason why we work with co-monotone operators is just for completeness. We didn't think that it will be useful sometimes because monotone operators seem to be more useful. And we're glad that it turns out that we were wrong. The co-monotone operators also plays a role when we later work on a different project on the ADMM. So let me continue with the adaptive ADMM. So how much time do I have now? I think I can have
it's
5 more minutes.
Yeah, 5.
Okay, I'll try. Okay. So the ADMM, the classical ADMM, is a well-studied splitting algorithm for the optimization problem of minimizing fx plus gz, where X and Z are related by a matrix relation, Mx equals Z. And the ADMM generated by this sequence, xk plus 1 is a minimum of the augmented Lagrangian. L gamma is defined by this expression. So many of you may be already familiar with the ADMM, but some of you may see it for the first time. But anyway, ADMM is just so popular and so successful in many applications and has been studied very well in the literatures. And what we did is we modify the parameters. Okay, let me go back to, well, I need to emphasize here. You can see the parameters gamma appears in both expression, in both relation, okay, the same gamma. The ADMM, the adaptive ADMM, we will modify these two parameters. One is gamma and one is delta. Okay, and for these two, we will make a connection to the Douglas-Rachford algorithms. I think, well, I can move on to the application of that is we will apply to the minimization problems of Whitley's convex function and a strongly convex function. So f is alpha convex if f minus alpha half of the norm square is convex, or equivalently, you can write down the expression. And if alpha greater than 0, we have strongly convex. Alpha less than 0, we have weakly convex. So some other concept called coercive, super coercive, and it is known as strong convexity, implies super coercivity, and implies coercivity. These are pretty standard in convex analysis. Right. And some more definition, the Fréchet subdifferential, I think I can skip that, the recession function and the Fenchel conjugate. Some of these, many of these we will use to put in our summarized result. So here is the big result that we obtained from the work with Ruben and Sadie. We will minimize the sum of the function, the sum f plus g, where f is alpha convex, g is beta convex, such that this blue condition is satisfied. This is the critical, that f is always strong, or at least strong, okay? Strong or monotone, of course, well, or convex. And this is like a weak counterpart. And we cannot flip the role. That's one thing. The second thing is we have collected several assumptions that has been used for the ADMM in the literature, and we hope we have done a thorough job. Pretty much that we collect from many works, but there might be a chance that we miss someone's work. We will fix that in the future. So if one of the condition in the group A is satisfied, and if one of the condition in group B satisfied, okay, then, and we choose appropriate parameters, gamma and delta, then the sequence generated by the adaptive ADMM will converge to a critical point of the Lagrangian, for which we will find a solution of the original problem. That's the main result in this papers. And the idea of the proof for this is we define two new operators, and this is has been observed for the classical ADMM. For our work, it turns out that under the assumption made, the operator Q is maximally co-monotone, strongly monotone, and the operator S is maximally beta co-monotone. That satisfies the sum of the two parameters greater than 0. And so we can apply the adaptive DR to the two comonotone operator and obtain our result. Okay? And we have put quite a few work in to guarantee these two condition works, and it is quite subtle, and we I think we pretty satisfied with the current results that we obtain. And I think that's all I have. Here's some references for the Douglas-Rachford algorithm, and here is an incomplete collection of papers on the ADMM. And thank you for your time. And I'm happy to answer any questions.
Thank you, Hùng, for the very nice talk and very detailed. And now's the time for questions. So if you have any question or comment, please unmute yourself and ask. Matt?
Yeah, can I ask it? Thanks for your talk, Hùng. Really interesting. I have one question, not about any particular result, but just about the kind of overall kind of strategy. So you always have this situation where you have that the sum of two operators is monotone, even though the individual operators themselves might not be monotone, or like alpha monotone with alpha bigger than 0, right? And you always need to know what that alpha or the beta is in order to choose the parameters for the algorithm. Could you imagine adapting this in some way so that if you didn't know what alpha and beta were, it could still work so long as the sum was maximally monotone, say?
Mm-hmm. Well, thank you for your question. Actually, that is a very practical question, because in practice, we usually don't know alpha or beta, right? Well, if we don't know alpha or beta, at least we need to know something before we can actually do something, right? Otherwise, we're going to run a plain vanilla of the Douglas-Rachford, and let's see where it leads to. But on top of my head, I don't think I have anything to provide if we don't know the parameters. There's not much so far. There's not much I can do. I would say I have nothing to proceed. I mean, it's not possible for us to proceed with the current techniques approved. Maybe if someone can observe a few iterations and then try to adjust the parameters based on the information in the past, that would be a possible direction of research. But so far we haven't proceeded, or we haven't got any result in that direction. But that is very interesting and approach, I think, and may be possible, but I don't know.
So it seems like maybe like what you're kind of alluding to is a kind of line search sort of thing, but with resolvents instead of.
Yeah, that's right. And that's I think it may be a more practical way to proceed with unknown information that you need to observe. Let's say you observe 20 iterations, and then you decide, okay, I have to fix that. But we don't have any concrete result on that direction just yet. Maybe somebody else can work on that.
Okay. Thanks very much.
Okay, thanks much. And we have next question from Gary.
Thanks for the talk, Hùng. In my mind, one of the real strengths of the Douglas-Rachford algorithm is that if there's no solution, the iterates will diverge. With your adaptive Douglas-Rachford, do you still preserve divergence if the solution set is empty?
Well, thank you for your question. That's actually very interesting. And so far, we haven't observed the behavior for the inconsistent case. That is something that we might want to do in the future. The reason for us to proceed with this, at the very least, we want to proceed theoretically. Let's see how the theory, how far we can push in the theoretical direction. But certainly, that is still very open. Whether when you have the inconsistent case, can we still have divergence of the sequence or convergence of the shadow? That we don't know, unfortunately. We hope to come to investigate the question in the near future, and we were very open for suggestion or collaboration on that front. Thank you, Gary.
Thank you.
Okay. Okay. Thank you. Any other question or comment? Maybe I have one question. It seems that for the adaptive ADMM, you working on finite dimension.
Oh yes, yes. For the adaptive ADMM, we have a matrix instead of a linear operators. We decide that we're going to go with the finite dimension first. I think it's also possible to extend it into infinite settings, but for us, we want to make sure that it works nicely, so that we decide for now we work with finite dimensions.
Okay. Okay. Thank you. Any other question or comment? So if not, so let thank the speaker again. Thank you, Hong, so much for today.
Thank you all for staying with the talk, and I hope you have